This is part 2 of the Gauss's law notes. This video actually will talk about flux, and we will go through pages 4 through 6 in the notes section. So what you're going to see throughout this unit are 3 fundamental symmetries that we're going to see over and over again. We'll see a planar symmetry, such as a plate full of many charged particles. We'll see a cylinder, such as the one you see here, with the electric field going perpendicular to the surface, and then we will see a spherical symmetry. We're going to use these, and you're going to have internet homework over a sphere, internet homework over a cylinder, and internet homework over a plane. And hopefully you'll take this in little bitty chunks so it doesn't get overwhelming. That at least is my goal. When you see planar symmetries, when we have a parallel plate capacitor, a cylinder is going to be a coax cable. Again, this is another type of capacitor that we'll talk about here in a little bit more detail in the next couple of units. And then a spherical symmetry we're going to use so much that you're going to get sick of it. We're going to talk about a new term. This new term is called flux. The symbol that we use for flux is phi. It is the Greek symbol with a circle through a line surrounding it. And so what would we define flux to be? And so if you will look at this diagram here, if I have a certain area, we will have some electric field lines going through that. And the amount of that electric field depends upon the strength of that electric field. The stronger the electric field is, the more lines that pass through that given area. The surface area also depends upon the flux. If we have a greater area, we will have more flux lines going through there. And finally, the angle with which it goes through. And so we will always have to use perpendicular components here. So the electric field has to be perpendicular to the area. If it's not, we have to use that component that is perpendicular. So again, this goes into that being perpendicular to the surface. And if we look at theta here will be the angle between the area vector, if we make it perpendicular to our area, and our electric field. And so this becomes the formula right here for the electric flux. It is E dot dA, and that dot's a dot product. Those of you in calculus might have done dot products. If not, what it means is we have to be perpendicular to one another. And so the flux is defined as EA times the cosine of theta. So make sure you are using that cosine component. If we have a very difficult shape such as a banana, we will have to integrate that, and we'll integrate E dot dA. We take a bunch of little areas and we add them all up. So if we go back to our notes and look at this flux, we can see this box. And this box right here, notice that the electric field is leaving the box. So if it is leaving the box, just like we learned before, the electric field always points from positive to the negative. The arrows go from positive to negative. So this must tell me that there is a positive charge inside of here because the electric field is leaving. In this case, my arrows are going inward. Since my arrows are going inward, this charge inside of here must be negative. Notice that my electric field lines are completely passing through here, so there must be no net charge inside of here because the positives must be on the outside as my electric field goes through there. So what is a Gaussian surface? A Gaussian surface is a closed surface through which the electric field passes. The surface has to be in 3 dimensions, and the electric field or some component must be perpendicular to that, and it must have the same magnitude on each point on the surface. Picking the right Gaussian surface is the secret, and we're going to work enough of these problems that you're going to know exactly which Gaussian surface to use. As you saw before, a banana is not going to be a good Gaussian surface to use. Most of the time it's going to either be a sphere, a cylinder, or a plate. So here we have a cubic Gaussian surface, we have a cylinder Gaussian surface, and 2-dimensional things. Okay, so right here we have a Gaussian surface that goes through here. This is not very helpful because the electric field lines are not the same all the way through. So we would want to have the electric field being the same all the way through. This one's not enclosed, so everything's coming out of it, and so that won't help us very much. So The electric flux is the amount of electric field passing through a given area. If it's an outward flux, it is a positive charge. Just like we saw before, if our lines are going out like this has to be a positive charge because it goes from a positive to negative. If it's a negative charge, my flux is going to have to be going inward. And if there's no net flux through a closed surface, there is no net charge. Again, how do we calculate that electric flux? The area must be perpendicular to my electric field lines. If it is not, then we will not have any flux. Now we can get a component that's perpendicular, and that will allow us to have some flux, but in this case, the flux would be 0 because the area is in the same direction of the electric field. This would be a maximum flux value because they're absolutely perpendicular, and on this one we would have to take this cosine component to get this flux. So here's the formula. The flux is defined as E dot dA, and if it's at an angle we will use that cosine of theta. Two 100 centimeter pair electrodes are spaced 2 centimeters apart. One is charged to 5 nanocoulombs, the other -5. A 1 by 1 centimeter surface between them is tilted to where the angle makes a 45 degree. What is the electric flux through this? Okay, so what the heck are we going to do? We've got two parallel plates that are 2 centimeters apart. They're charged to 5 nanocoulomb, the other to -5, and we've got a surface between them. So here's our picture. I've got two parallel plates here. What do we know is going to be between those parallel plates? Hopefully you realize that there is going to be an electric field between those parallel plates. And so in order to do this, I need to know what that electric field is, because in order to do flux, I have to have E dot dA. I've got the area because I know what's going to be between them. I somehow have to get that electric field. And so how am I going to get that electric field? I am thinking on how I get that electric field. And so let me pause this and then I will come back because I'm not exactly sure. Okay, here's the problem on this. Where I got this problem from this book, they made you memorize how to calculate the electric field with a single formula between these parallel plates. I'm not going to make you do that because you don't need to do that on the AP test. What you do need to know is what that electric field is. So that electric field is going to be 5.65 times 10 to the 6 newtons per coulomb. Again, don't freak out about this. This will be given in the problem. So in order to calculate this electric flux, I'm going to take this electric field, 5.65 times 10 to the 6th, and I'm going to take my area. Notice it's in centimeters. We don't need to be in centimeters. We need to be in meters. So it's going to be 0.01 times 0.01, and we need to look. Is it at an angle? Yes. So I have to take the cosine of that angle. And so when I do that math, I should get an electric flux equal to 4. And the units here, what's the electric field? Newton per coulomb. Area is going to be meter squared. So it's going to be a Newton meter squared per coulomb. Again, the formula for electric flux, E dot dA, not too bad. The electric flux of a non-uniform field. If our electric field was constant over the above surface, if it's not, we have to take them into little bitty pieces like they did on the banana and integrate, and we'll have to add them all up. And once we do that, we will get the total flux. Okay, so again, this is how we need to calculate flux. Formula is simple. The formula is for flux is E times area. Make sure those are perpendicular to each other. If they're not, you have to take the cosine component of that. All right, that concludes this lesson. Go work some internet problems and see if you can do them.